Yes, so in our previous lecture, we have looked at how hill climbing works, and we have understood that it is a heuristic algorithm, okay, based on different heuristic functions, and it's an efficient algorithm. Now we look at this algorithm more formally, like the characteristic, the aspects of this algorithm. So is it a complete algorithm? No, it is not a complete algorithm, because you have seen that when we are doing that heuristic function evaluation for that block domain problem, we didn't reach the goal, right? So it doesn't ensure that it will reach the goal. Quality of solution is also debatable, but it will majorly depend on the heuristic function. So if your heuristic function is good, like you saw that we took two heuristic function, and one heuristic function was more discriminating, so for that we actually could reach the goal. Okay, so it depends on what kind of heuristic function we are picking up. Space complexity. So I think space complexity is one of the major advantages of hill climbing algorithm, because it just stores the best value, right? uh, so whatever we have explored so far, it just stores the best value. There is no nothing like backtracking. Just 1 minute. I think someone is trying to join. Yes. Let me admit Krishna. Okay. All right, and then we have this time complexity. So time complexity wise also it is linear, right? Because you are only looking at a node and then exploring its neighbors, right? So that way also time complexity also it is linear. Okay, now you understood the problems of hill climbing, right? So what was the major problem that we discussed? The major problem was that you can get stuck at the local maxima, right, or local optima. So if you have started your journey from here, you will reach somewhere here and you will think that this is the optimal position, right? So this is something we need to get around. Okay, uh, so for that, let's understand another problem. Okay, so this is one of the problems which has exponential complexity, okay, which is called as satisfiability problem or sat problem. Okay, so look at this problem carefully, and you know that I am mostly following the book by Deepak Khemani, right? So for detailed study you can look at that book. So satisfiability problem is like this. I think someone else is joining. Yes. So satisfiability problem is like this: that you have a Boolean formula made up of a set of propositional variables, right? So and they are combined in different manners. So you see the conjunction, the disjunction, the negation operators, right? And what you need to find out is you need to find out that what values of this A B C D E, okay, actually makes this final expression f to be true. Okay, so that you call as, so what satisfies this particular formula. Okay, so what you try to do over here is you try to, or what is your solution space here? So if you have 5 variables, you can understand that they can take values 0 and 1. So each variable it can take 2 values, so 2 to the power 5 possible set of values A B C D E can take, right? And the problem is, or the question that is given to you is that find those values of A B C D E which makes f as true, or the value of f as 1. Okay, so is this part clear to you?
Yes, sir.
Okay, now why again we are interested in this problem, or why we study this problem? So if you remember the Alan Rich's definition of AI, what we said was that one of the objective is to write programs or find solutions which were earlier exponential, but now you can solve them in polynomial time, right? So that was one of the objectives. And the so SAT problem falls into this exponential problem, because if you have n variables, then number of solution possible is 2 to the power n. Okay, and if you calculate, like if you take maybe 1000 binary variables, which may be possible, right, if you are looking at a complex circuit, right, and if you try to find out that if you have 2 to the power 1000 such possible assignments or such possible values of a b c d e, and your computer actually can execute or can evaluate 10 to the power 8 such solutions per second. So this is the roughly the number of seconds you are going to take. Okay, and if you do some basic calculation, you will see that it will run in thousands of years. Okay, so these kind of problems are of interest in AI, and now we will try to see that how we can think of some heuristic functions, and how you can look at hill climbing in the context of SAT problem. So SAT problem will again revisit for different other algorithms, like we always revisit TSP, traveling salesman problem. Okay, so this is some of the benchmark problem which has a very high solution space. Okay, which are some of the target problems. Okay, and yeah, so SAT is one of the earliest problem to be proven NP complete, and you see that solving the SAT problem by brute force can be unviable when the number of variables is large. Okay, so a formula with 100 variables with will have 2 to the power 100 or about 10 to the power 30 candidate assignments. So even if you take 10 to the power 30 like 100 variables, which is roughly 10 to the power 30, right? So 10 to the power 30 by 10 to the power 8, it will give you 10 to the power 22 seconds. Just think of the magnitude that will get from there. Okay, so now what we are going to look at is, there is a one solution which tells that you can change the concept of neighborhood. So if you remember that we have looked at this function moveGen, which takes a state as an input and generates its neighboring states, right? So that's all we know. And we also know that hill climbing is a greedy algorithm. So what it tries to do, it tries to exploit, it doesn't try to explore. And because of this nature of exploitation, it has a tendency to get stuck in the local minima. Okay, so that is the problem. So wherever we are trying to come up with a solution for hill climbings getting trapped in the local minima, you try to add some feature on the exploration side. Okay, so one of the things can be that instead of looking at a certain amount of neighbors, I can try to increase the concept of neighborhood. Okay, so before that, let me tell you this. Okay, that let's say your expression has 5 literals. Okay, and let us say that A, B, C, D are the literals and A and C are true. Okay, so how to represent the solution? So we represent the solution like this. Okay, so please understand this. Okay, so this is the solution. This is the binary string by which we represent the solution. Okay, and now here is something I want you to think. So what will be a solution which is neighboring to this solution? Okay, so let me repeat the question. So I know that this is the solution, so maybe this is the state I am currently in. Okay, and I want to generate its neighboring states or neighboring solutions, however I want to put it, right? Now what will be your intuition, that what are your neighboring states, or what are your neighboring solutions? Okay,
So flipping one bit.
yes, so the best or easiest way is flipping of one bit. Okay, so I can go one by one and change that bit, so it is still quite near to what we have in the solution. Okay, so if you have 10100, so first you flip the first bit. Okay, so it is changed from 1 to 0 over here. Okay, so this is changed. Now you go to the next bit. Okay, I think this is not correct, so it will be 1 over here. Okay, this should be 1, and this is now flipped, you see. you go to the next one, right? The third bit is flipped, all others are intact, fourth one, and so on and so forth, right? So basically I will go bit by bit, and for each of my neighboring states, so this is how you will generate your move gen. So for each of the neighboring states, you take one bit and you flip it, all other bits remain intact. Okay, so now this we call as one bit neighborhood. Okay, so this is called as one bit neighborhood. Okay, one bit neighborhood. Now one thing is there, that as I said, that what I want actually in hill climbing. So basically when I am here, let's say, I what is happening is I am taking a step like this, right? I am taking a step like this, and I'm getting stuck over here. I cannot actually move along. Okay, but if I somehow can take a larger step and somehow reach here directly, okay, so then what can happen? I can actually go to this, right? So this is the intention behind increasing the neighborhood size. So in this case, instead of using your one bit neighborhood, what you can do is you can use 2-bit neighborhood. Okay, so what is the meaning of 2-bit neighborhood? That at a point of time you randomly choose any 2 bits. Okay, so how many possible bits are there, or how many bits are there? 5. Okay, so you are going to choose any 2 positions, so it is going to be 5c2, right? So actually you can generate so many. So this is 10, right? 5 into 4 by 2, so this is 10, and actually you will have 10 neighbors when you increase from 1-bit neighborhood to 2-bit neighborhood. Is it clear to you?
Yes, sir.
Yeah, so
Yes.
first of all we understood that what is the need of increasing the neighborhood, and then we also understood that how when we change to 1-bit to 2-bit neighborhood, how the neighbors will be generated. So that's what we have done here. So initially these first two are selected, right? So this is flipped, you see, 1 has been flipped to 0, 0 has been flipped to 1, and rest are intact, right? Okay, so similarly next one, what has happened is next 2 are flipped, okay, you see, and other 3 are intact, and so on and so forth. So that's how I generated the neighbors. And there is of course a amount of caution, because when you increase the neighborhood, actually the advantage of hill climbing starts going down little bit, because now you are dealing with a much larger solutions to compare with. Are you understanding? So at a worst case, if I make this a neighborhood, what will happen? So all the solutions now will be my neighbor, right? So that is something of course we don't want, right? So 1-bit neighborhood is best, and you can go to 2-bit, but more than that it is not very much recommended. Okay, unless you really have a very very large solution space. Okay, so that is one thing that I want to tell you. And here when I am saying 1-bit or 1-bit or 2-bit neighborhood, so what I'm assuming is that we have encoded the solution as a binary string. Okay, so more generic term for this will be one literal neighborhood, because you could have represented it, maybe it is a genomic sequence, and you have represented it like AGCT, something of that sort, right? Okay, so then it will be one literal change, not 1-bit change, right? One position change basically. Okay, all right. So how this I can use this in context of hill climbing. So what I'll do is I will start like I start in hill climbing, right? So I will put the start in node. I start with this assignment, and then I'm going to create a loop. Okay, and here what is happening is that every time I am changing my move gen function. So basically let's say your n is 5. Okay, let's say your n is 5. So what you are essentially doing is, first you are going with a 1-bit neighborhood, then you are going with a 2-bit neighborhood, 3-bit neighborhood, and so on and so forth, and then you are with that move gen function you are running hill climbing. So basically what you are doing is you are running your hill climbing for 1 bit neighborhood, 2 bit neighborhood, 3 bit neighborhood, 4 bit neighborhood, and so on and so forth, and basically returning the best result. And that's how you are strategizing to actually escape the local minima. Is it clear to you? Hello?
Sir, n here represents how many bits we are flipping in
Absolutely,
each time we are
absolutely,
running it.
absolutely,
Okay, sir.
absolutely,
Okay, sir.
absolutely.
Okay, sir.
Yeah, yeah. So is it clear to others also?
Yes, sir.
Okay, okay. All right. Now, before I proceed, so actually, I think it was 2018 or 918 maybe. So we wrote a paper on, hill climbing for feature selection. Okay. So it is a book chapter actually, and I later on I can share that book chapter with you. So there we tried to actually give a taxonomy of hill climbing techniques. Okay. So this is important for you to understand. Okay. Pay attention. So what we have looked at is, what we are looked at over here is that, we have understood that we are going to steepest ascent. Okay, so what do I mean by steepest ascent is, let's say, my heuristic value, better is the solution. Let's assume that. And let's assume that you have you are in a node where the heuristic value is 5. Okay. And you have neighboring nodes, right? So maybe this has heuristic value 3, maybe this has heuristic value of 10, and let's say I have another one which has heuristic value of 8, and I have another node which has heuristic value of 6. Okay. Now what is happening in hill climbing where I am going from 5? So when my neighbors has these heuristic values, where I am going from 5, which node I will go to?
Has the highest value.
Which has the highest value, right?
Value.
So others also please understand this. So I will go here. Okay. So this is giving me steepest ascent. So this is what is my steepest ascent. Okay. Did you understand? So that's what we have studied. But and one of the things with steepest ascent gradient descent is that it is deterministic. So if you start your algorithm with a particular start node, you will reach a particular node at the end. Okay, so there will be no difference in that. Okay, so this is stochastic. All right. And another option is, if you see, is random best or next best. Okay, so do you know what is the meaning of random best? So basically now what will happen is that I can go to any of these nodes with certain probability. Are you getting me? So basically, maybe if I let's say ignore that, let's say I will not go to some place where my heuristic value goes down, but I have, so here the gain in heuristic value is 5, here the gain in heuristic value is 3, and here the gain is 1. Is it clear? So what I will do is, roughly, that I can make a probability distribution where I will go to the node where the heuristic value is 10 with this probability 5 by 9, and similarly I will go to 3 with the probability 3 by 9. Okay, and similarly I will go to maybe this node 6 with probability 1 by 9. Okay, is it clear to you?
Yes, sir.
So now that's why we call it as random based. Okay, it is a random based neighbor, and now it is not a deterministic algorithm, it is a stochastic algorithm, because in what step what neighbor will be selected is something you don't know. Okay. Now another thing at this point of time you need to know is that, let's say I tell that here is a problem statement that move from node I, okay, move from node I to node J, okay, sorry, node I to node J with probability 60%. Okay, so can you tell me how to convert this into a into your code? Okay, and I want now to hear from someone else. Okay, so have you understood the problem? That what I've asked you to write in a code is that move from node I to node j with probability of 60%. Okay, Shondip, is the problem clear to you?
Yes, sir.
Yes.
But
Yes. So can you tell me that how can you write it in a program?
sir, node I to node j with probability 60%, right?
Yes. Yes. So don't think about the
There will
syntax.
be only two.
Yes. Yeah, there are only two nodes.
Yeah, so first one is I and second one is j,
Correct.
and the probability from I to j would be like 6 by 10, so that would be like 3 by 5.
No, but that is right. But how will you make this right? That it will move by 60% probability.
So, sir, if I run 5 loops, 3 times I will reach to j and 3 times I won't reach to j.
So how will you
So
write
that
the
would be the
five
solution.
loops? That's the question. So when you are
So I
actually
guess,
when you are actually running the
I
algorithm,
will.
yes, yes.
Yeah, sir. I was telling that, sir, I will traverse through in order. In order traversal I can use.
How that will help you? Well, please pay attention to
Sir,
the
through in order
60%.
traversal I can use from five.
See, please pay attention to the 60% probability that there is no loop. I am saying that when I execute this program multiple times, okay, so there is no
Sir,
loop
can
within
I
the
speak?
program. There is no loop
So can
within
I?
the program. Yes, just one second.
Okay, okay, sir.
Yeah, so there is no loop in the program. So what I'm saying is that if I run this program 10 times, 6 times it will move from I to j, 4 times it will stay in I. Yes, you can say Aritra.
Sir, can we just pick a random number between 1 to
Yes,
10?
yes. So so
And
so
then
so
if the number
you are
falls
right.
between 1 to
Yeah,
6,
you are right. So what you have to do is you have to generate a random number between 1 to 10. Okay, so it will be like, generate a random number between, let's say, 1 to 10. Okay, and if the number that you are getting, and let's call this as r. Okay, so if r is, less than 7, right? If r is less than 7, then you uh, move I to j. Now it is not necessarily that you will have to put I less than 7. So any 6 consecutive values or even not consecutive values, because all are equally probable, right? And again, when you are generating random numbers, so as you said, Arithro, one of the things that when you go to the programming languages, you will have to look at is that what kind of distribution they are using for generating the random number. Okay, so if it is a normal distribution, then getting a value of 5 or 6 will be more compared to 1 or 10. Are you understanding?
yes, sir.
So when you are generating a random number, you are generating a random number with a uniform distribution. So coming, like, probability of anyone coming will have same probability. So like we have taken r less than 7, I could have taken that, when maybe r is greater than 4. Okay, so 5, 6, 7, 8, 9, 10, these 6 values. Okay, so that also would have been sufficed, right? Is it clear to everyone?
Yes, sir.
Okay. Now, so this is about this randomness of states, and now what we are going to discuss is that what is the direction of search. Okay, so when you are in a hill, okay, so uh, you can start from here, or you can start from here. Okay, so you can start from any of these places, and when you start from here, there is something called as forward. So let me explain again from the context of, let me again explain this in context of the SAT problem. I think it will be more easily understandable that way. So in forward search, what we'll do is we'll start with this initialization. We'll start with 0000, and then I will add 1 bits at a time. Okay, so that's why you call it forward direction, and so essentially as you move, the number of bits which are 1 will increase. Okay. And backward direction, as you can understand, it is just the other way round, and you start with 1 1 1 1 1. Okay, and then what you do is you flip ones to zeros, and that's how you go about it, and number of ones in this case reduces. Okay. And what is random? So random is basically, you start with you pick a string like this, right? One like the example that we saw earlier. So that was random. Okay, so that was random, and we were looking at 1 bit neighborhood of it. Okay, and we have already understood the neighborhood size basis of that. It can be 1 bit more than 1 bit, or 1 position more than 1 position. Okay, so so this is about different hill climbing searches that are possible within hill climbing. These are some of the varieties, and if you read the literature, if you read research papers, you will see that even there are more varieties than this. Okay, but these are the general ones. Okay, so you have already understood that even when you have thought about hill climbing, so what we are looking at is we want to somehow avoid getting stuck in the local minima. So one of the things that we have realized is we can increase the neighborhood size. Okay, because that will bring that will increase the neighborhood number of neighborhood solutions, as well as that will bring more diversity in the solutions. Okay, so one other way is that which is called as beam search. Okay, so beam search, what you do is, if you look at this diagram very carefully, okay, I think this is illustrated better in next this thing. Yeah, so here what is shown is that what is the starting node. So it's like a backward search that we are doing over here. Okay, it's a backward search that we are doing over here, you can see, and here are its neighboring nodes, right? So these are the neighboring nodes, and the values that you see over here are the heuristic values. So naturally, when there are 5 bits, so there are 5 neighbors, and you have calculated the neighboring heuristic values. Okay, so which one are better? These two are better, right? This one is better, okay, and this one is better. So hill climbing, what it would have done is it would have picked any one of them, right? So but in beam search, what is allowed is that you can actually keep 2 nodes. Okay, you can actually keep 2 nodes and explore them. So in next step, what is happening is you are again taking this and expanding, and you are seeing that okay, you have moved to 5 over here. Okay, and again here also you've got a solution 5, and that's how it proceeds. Okay, so you can understand that here you are actually checking more solutions than earlier possible. So earlier if it is a 1 bit neighborhood and number of neighbors were 5, you are only looking at 5 neighbors. Okay, but now when you are going to or when you are selecting 2 nodes like that, right, 2 best nodes, okay, then number of solutions you are looking at is 2 into n, right? So the solution space that you are exploring is double. So this is also a technique by which you are increasing the number of states that you want to explore as your neighboring states. Is it clear?
Sir, at each step we are choosing the best and the second best, or they must be equally best.
No. Best and second best. In this case, even incidentally they have same value, but it is best and second best. Okay, and this thing, right? So how many we are going to select is actually a kind of a hyperparameter that we talk, right? So this is called as beam width. Okay, how many we are going to select. So in this case we are using beam width of 2, but you could have picked 3 best neighbors also. Okay, so there is one more advancement. Okay, there is one more advancement of beam search, which is called as taboo search, which I am not discussing in the class, but I will request you that please read it up. Okay, so as you can hear, so taboo search means taboo, taboo is that you have certain kind of restriction or certain kind of feelings that you are not going to use them, right? So you have a taboo for something. Okay, so there what you do is you maintain a kind of a list, and where you try to see that if some solutions have not given you very good solutions, or okay, like if some states has not given you very good solutions, so you don't use it any further. Or you can also add a taboo that if you have visited that node in recent past, right, you don't again visit it, right, because you want your neighborhood to be as unexplored and as diverse as possible, so that you don't get stuck at the local minima, right? So taboo extends like that. And you will be surprised to know that beam search is used quite a lot in kind of parameter, like when you are trying to find optimal values of parameters, like hyperparameter optimizations. Okay, so beam search is used a lot even when you are dealing with some kind of audio data, right? So it has certain properties, okay, which has a temporal part in it, where you want the search technique to be very fast. Okay, so where you are trying to, so there is a word and you are trying to guess the next word. So there searches like hill climbing, beam search gives very good result, because these are efficient algorithms as far as time is concerned. Okay, all right. So another way of exploring more neighbors is called as iterated hill climbing. Okay, so by the name, does it suggest something to you? So iterated hill climbing is so basically you have, if you treat these search to be executed by different agents, right? uh, so you have a hill, and basically an agent is upscaling the hill, right? And every step it is checking how far it has reached and so on and so forth. So you can think of the search is being conducted by an agent, right? The person who is actually ascending the hill. Okay, and what you can do is actually you can take many persons. Okay, you can take many persons and make them start from different random points of the hill, right? And when you do that, what will happen? Definitely the quality of solution that you are going to get will be much better, right? Are you understanding?
Yes, sir.
Yeah. So this is what actually happens in iterated hill climbing, that you take multiple agents who start from different random positions. Okay, and one of the things that hill climbing lacks is, ideally, if let's say some of you are ascending the hill, right? So and one of the approaches can be that you do your hill climbing, right? You go up and do your hill climbing, and then once you have reached your respective peaks, right, you communicate that, okay, what are the respective peaks, and you take the best peak, right? So can you think of some way we can improve this? So what is our objective? Our objective is to get the best peak value, right? You agree with this? And that's the reason we are climbing the hill, right?
Yes, sir.
And we
Yes.
understood that instead of one person starting from some place and getting a peak, uh, it is much better if I take 4 or 5 of you, and all of you actually ascend from different random positions, and then if I compare the peak, I will have a more chance of getting a better peak, right? Right. Now what I'm saying is that this comparison, that what I'm doing is at the end. Okay, so what we could have done is, rather than that, we could have a communication mechanism, right? Communication mechanism in between, where the agents can communicate within each other. So Arithro finds that he is at 2000 feet, and Sarfaraz says that I am still at 200 feet. So then Aditya will tell Sarfaraz that you stop that terrain, you don't proceed there, because I am already at 2000. You come somewhere near to me and start exploring from there. Are you getting the idea? Right.
Yes, sir.
Right. So so that communication mechanism is not there in hill climbing, which you will see in PSO. It is there, right? but that can be one of the research ideas that where you can think of improving this algorithm. Okay, so now coming to iterated hill climbing. So you start with first a random node, right, and then you take that as base node, and then what you do is you again run a loop, and what you do is you for I equal to 1 to n, you generate a random candidate solution. So basically what you are doing is that if you have a terrain and if n equal to let's say 3, so maybe randomly you will get a value, or let me increase the terrain like this, something of that sort. Okay, so maybe one place you will get a value like this, right, another place will get a value like this, another place will get a value like this, right. So for all these 3 points you do the hill climbing. Okay, so that's what is happening here, that for all these n cases you do the hill climbing, and then finally you report the best node. Okay, so that's what is happening. Now please also understand that hill climbing doesn't have any dependency because there is no intermediate communication, as I said, right. So you can of course run this iterated hill climbing in parallel. Okay, is it clear?
Yes, sir.
Yeah, and basically what we are going to we are trying to tell you over here is just 1 minute. So basically this portion, okay, this portion, if you think that these are your different starting points and this is how your heuristic function is. Okay, so basically you want to start somewhere here. Okay, so this is often called as foothill. Okay, and essentially if you start anywhere here, then you are guaranteed to reach here. And what you want this shaded region to be with respect to the entire solution space, you want to be as large as possible, right. So that kind of tells you that for a particular problem, what is your probability to reach the optimal solution. Okay,
Sir, how do we define the foothill?
so basically it's more conceptual or ithro. Okay, so it's like looking at, so if you look at the solution space here, okay, like here we are looking at, so any position you pick in the solution space, where from if you do a gradient descent, you will reach the maximum value, so that is your foothill.
Okay, sir.
Okay. So next what we are going to read is we are going to read an algorithm called simulated annealing, and we'll stop today. Okay, so that's what we want to cover. Okay, so for that you have understood that one algorithm which really exploits is your hill climbing, right, which is completely greedy. And in another side you have an exploration algorithm which is called as random walk. Okay, so in random walk what you do is that you start with any solution and you take that as the best node, and then you run that random walk for many times. So it is not really a termination criteria. You are just saying that how many times you are running your random walk algorithm. How do you start? So you have already selected a node, and then you randomly choose one of the nodes. See, you are not looking at heuristic value. You are not making the probability of moving there proportional to the difference in the heuristic value. So nothing of that sort. You are just randomly choosing one of them, and then you are comparing that is your heuristic value better than what you have got earlier. If it is better, then you move to that node, else you continue. Are you getting what is happening? Is it clear?
So please can you repeat audio category?
Okay. So what I'm saying is that if you are, let's say, at a node 2 where the heuristic value is 2 rather, and then you have separate neighboring nodes, right? Okay, and let me not add many, so let's just have 3. Okay, so what I'm going to do is I'm going to randomly choose one of the neighbors if this is my starting node. If I, let's say this is my starting node, okay, and then what I'm doing is and let's say n equal to 5, something of that sort. Okay, so what I'm going to do is I have come here and I have randomly chosen one of the nodes. So maybe first time I have chosen this as 1. This node is picked up, right? Because it is randomly picked. So what will happen? It will check that is the heuristic value of this, this new node better than what I have. It is not, right? So there is no change. This if is not satisfied, right? So I will be incremented. Now for I equal to 2, then it will randomly choose another node. And now probably it may choose this one, right? So here it will check that, okay, is my solution better than what I had earlier? So it is better. So now my solution will move here. Okay, and again it has some neighbors, right? It may have 6, it may have 7, okay, it may have 8, like this. Okay, and what it will do is it will see that, okay, maybe 6 is chosen, so it will move to 6. Okay, and again I will be incremented to 3. So that's how it will proceed. So in a random walk you generally never converge. So as many iterations you run, you have more probability of getting a better solution. Is it clear to you now?
Yes, sir.
Yes. So at one end you have hill climbing, which is completely greedy and exploiting. Another extent you have random walk, which is kind of completely random. It has nothing of exploitation sort. Okay. So there is an algorithm which came like in 1980s and become very, very famous, is known as simulated annealing, and which tries to somehow combine these concepts of random walk and hill climbing. Okay, so that's the reason you need to be introduced to random walk. Okay, all right. So it's a very powerful technique, as I said, which combines both exploration and exploitation. And annealing, this analogy comes from thermodynamics, okay, especially with the way that metal cools and anneal, right? And so every state has an energy state, and the optimal solution here is metaphored as the lowest energy state. Okay, and what you are trying to do is you are trying to change the temperature, so that it goes to the lower energy state. So temperature is a tuning parameter. Okay, and this is very, very generic, can be applied for many techniques. Okay, and as I said, that the lowest energy state metaphors the optimal solution, and temperature is the tuning parameter. Okay, so we will understand this, why this concept of tuning parameter is coming. So this tuning parameter has a role to decide that in your search how much you will be random and how much you will be greedy. Okay, so that's the reason we are talking about this tuning parameter. Okay, all right. So this thing we have already kind of discussed. Okay, that let's say you are at a node C. Okay, and now instead of using this heuristic value, we are indicating this by the energy state or energy that is available. Okay, so this C to B, right? C to B is the difference in energy is represented by this, right? Delta E BC. Okay, similarly it is represented, this difference between A and C is represented by delta E AC. Okay, now simply what we are discussing in stochastic hill climbing, here also what we are saying is that probability of moving from C to A or C to B, okay, is proportional to C to A is proportional to del E AC, and C to B is proportional to del E BC. Is it clear? Okay.
Yes, sir.
Yes. So now this is a randomized algorithm. Okay, and one of the randomized algorithm that we have seen so far is your stochastic hill climbing. Okay, so simulated annealing actually adds a dimension to it. Okay, so what it does is, this is very important, that it starts off being closer to random walk. Okay, so if you are in a terrain, you can go from one place to another just like that. Okay, and once gradually when you are seeing that you are getting better solution, then you do something like hill climbing. So initially you are not greedy, initially you are exploring, you are trying to find out which hill is better and all, and then you are becoming greedy. Okay, so now this changing behavior, as I said, is controlled by a parameter parameter T called temperature. Okay. So like like we see for gases, so we associate high temperatures with random behavior, like much like movement of molecules in physical material. Okay. And so we want to start random, right? So what will be the temperature value then for our algorithm? It will be a high value, right? And gradually we will make it smaller and smaller, so it becomes more deterministic. Okay. And it is not as simple as I said in case of it is not as simple as I said in case of your this stochastic hill climbing. Here the probability of moving from current node to the next node is given like this, which the probability is given like this, which is 1 by 1 plus e to the power minus delta E by T. So this is a probability, and you can understand that this will always have a value between 0 to 1, right? Okay. So can you tell me that if they have same same energy value, right, the current node and neighboring node, so what should be the probability of moving there? Did you understand the question? So ideally, if current node
delta E will be 0.
yes, no, don't think of
because both of
don't think of delta E. I'm saying from a common sense point of view, right? So if you are in current node and next node also has heuristic value same, then you should have a probability of moving there, like probability of moving there with 0.5 probability, right?
Yes, sir.
Right. So that is what even if you put 0 over here, that's what you will get, right? And let's say that your del E is very, very high. Okay, so if del E is very, very high, then what will be this value? So it will be like T by e to the power delta E, right? Or
Yes,
or
sir.
1 by T e to the power delta E. So it will be, if delta E is very high, this will move to 0, right?
Yeah.
Yes,
So
yes, sir.
if the energy difference is very high, it will move to a probability with like probability of 1. So it will move almost deterministically, right? So that's how it is working. That's the interpretation. And what will happen, if delta is very, very small?
It will have lesser probability of going there.
It will have a very lesser probability, right? You got that, right? Yeah. So this is what now also there is something to do with t equal to 0 and t equal to infinity, but this is where you have drawn. So this y axis that you see over here is your probability, and this is your daily. Okay. So, and for a particular value of t, okay, you pick a particular value of t, and this is how your shape changes. So what does that mean is that as daily increases, right, as daily increases, so essentially if you are at a particular value, okay, and you are going to like you have started from 0, so this is actually negative of daily and this is positive. Okay, so basically what I am saying is that moving to somewhere where daily increases, the probability is more, right? And when you have a less value, you still have some probability. You still have some probability, but the probability is less. Okay, is it clear? Now,
Yes, sir.
now think of the effect of t. Okay, so what I said, as t becomes infinity, what will happen is that you will see maybe you will have a graph like this, because it is like random walk. So going to something negative will have equal probability, going to something positive will also have equal probability, something of that sort. Are you getting me? And when t equal to 0, it is like completely, so when you have when your energy is getting increased, you have a probability of 1, and when you are getting decreased, your probability is 0. Okay, is it clear what will be the effect of t? So now if you have understood the effect of
আরেকবার বলবেন?
so basically what I am saying is that when t is having a small value, okay, then as I said, that it is very deterministic. Then if I am a current node and my neighboring node has a higher energy value, I'll move with a probability of 1. Mane t, these curves actually represent smaller value of t. Okay, and as you move the value of t, then your shape of the curve changes like this, right? So when you have a higher value of t, what is happening is that moving to somewhere where your energy is higher, this is much less steeper because it is more random. And as you have smaller value of t, you see it is more deterministic because it is much steeper. Is it clear?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Okay. So now coming to simulated annealing algorithm. So this is just just does that. So what it does is it starts with some random node like we always do, okay, and we assign that to be the base node. Then we give t, the parameter t, some value, right, some large value, you see, and then I run the algorithm for few number of epochs. Okay, so actually these epochs will run for different values of t. Okay, and then within that value of t, there will be a search algorithm every time happening. So what I'm going to do is I'm going to look at a neighbor. How do I do that? I check a random neighbor, okay, random neighbor of node, any random neighbor, and then I calculate this daily. How do I calculate this daily? I evaluate the energy state of the neighbor and I evaluate the energy state of the current node. And then as we discussed about this randomness, so you see that's what we are doing. If random, we are generating a value of 0 to 1, and if it is less than this probability, like 1 by 1 plus e to the power minus daily by t, then we move to the neighbor, right? And then we also see that if the eval of the node is best better than the best node, then we make it the best node, right? Okay, and
Yes, sir.
and we change now t. So every time I run the loop, I change the t little bit, so I cool it down, right? I anneal. Okay, so I start with a high value of t and then I gradually reduce it and cool it down. So initially when I have a high value of t, my movements are very random, and then now when I am getting good solutions, or I am close to convergence, I don't allow it to explore randomly. Now it kind of saturates there. Okay, so that's how actually your simulated annealing works. So I think you have to so this is a little bit maybe intense. Okay, so you have to really go through these slides, okay, and then next class we'll take another important algorithm which is called as genetic algorithm. Okay, so we'll do genetic algorithm and PSO, and then we'll move to our machine learning and deep learning part. Okay, so which I think many of you have some idea already.